Well, welcome back. Once again, this is Benjamin Nusz, MREA instructor and Midstate Technical College instructor. And in this session, we're going to be talking about system siting and design. So we're going to look at first the proper areas for placement of the collector array to ensure that it receives maximum sun and achieves maximum production. And then we'll look at some of the basic sizing and maintenance guidelines that are out there as well. Now, first we have to discuss what our target is. And we mentioned previously about the solar fraction. And the solar fraction is the percentage of your total load that the solar thermal system will be able to deliver. Now, it's very challenging for anyone in northern climates or in middle climates to achieve 100% solar fraction. The limiting factor isn't the cold temperatures. It's just simply the amount of solar radiation that we're going to receive. We just have too many cloudy days. The target or the normal guidelines that we have is that one sunny day should be sufficient to heat up your tank. However, if you do not have a sunny day, then you will need your backup to kick on. In most climates in the United States, this means that we're normally around 75% of the total annual load. Some will be around kind of a 50 to 75% range, but our target is always about 3/4. In the summertime, it's very easy to heat almost all of the hot water that you use, but in the wintertime, we have too many cloudy days. And it's not just a matter of every other day being cloudy. We have long stretches of cloudy weather. So we can't just simply oversize the system and bank it for those cloudy days, because sometimes we have as many as 5, 10. In Wisconsin, our record is 22 straight days without significant solar producing sun. So we want to just kind of design systems with backups and accept that we're going to achieve the highest solar fraction that we can do. Now, again, that's going to heat up our tank to around 120 to 160 degrees. That's what we mean by a fully sunny day. But remember that if you've only got sun for a couple of hours, it's still going to be contributing, just maybe not 100% of that day's consumption. So where we want to start is first with some form of a site analysis. Now, we have a full course on site assessment where we look at this in a lot more detail, look at how to use all these tools. And so here we're just going to be introducing the concepts so that you can get a general sense of where's the best location for these. Now, first we want to figure out whether we're going to be suitable on the ground or on the roof mount. And we looked at on a previous collector mounting session about all of the potential places that there are. So analyze your site and figure out, do you have a place that's roughly going to be about 10 feet by 10 feet where you can fit a couple of collectors. Now, we want to make sure that, of course, it gets as much sun as possible. And we refer to this as the solar window, is the kind of imaginary window in the sky that the sun will be passing through. Now, the bottom of that window will be defined by the lowest path of the sun, in other words, the winter solstice. And then the upper path is the highest path of the sun, or the upper bounds of this window. Now, we put edges on this window of about 9 a.m. to 3 p.m., and those are really our critical times. Early in the morning and late in the day, we will actually receive very little production. Now, with solar electric systems or PV systems, they will oftentimes be installed on trackers, a single axis or dual axis tracker that follows the sun throughout the day and follows it seasonally. We tend to not install that type of equipment with solar thermal systems for two important reasons. The first is that solar thermal collectors tend to be heavier, and also we're using a rigid pipe. Now, that stainless steel flexible pipe is flexible, but it becomes rigid over time and is not intended to be moved back and forth, and it becomes brittle and gets stressed very rapidly if it ends up getting moved quite a bit. So we really have some technical limitations that certainly can be avoided with some tubes or some piping that would have to be regularly maintained or repaired. but it's really a technical problem that we have. It takes a lot more energy to move a higher weight collector as well. But the other reason is that there is very little energy to gain in the morning, and oftentimes it's too low that it doesn't exceed a minimum threshold. With solar electric, there is no minimum threshold. As long as you're able to kick the inverter on and a little bit of sunlight's hitting it, you'll generate a small amount of power. With solar thermal, we can't actually turn our system on until the temperature in the collector exceeds the temperature in the tank. Generally, that means it's got to get up to about 80 or 90 degrees before our pump will even kick on. So that early morning sun, where it's just doesn't have the intensity, we're not meeting that minimum threshold. Sure, some sunlight is falling on the collector, but it's not getting it up to an appropriate temperature. So generally, we tend to have our collectors fixed in a certain place, and we are then therefore less concerned about early morning sun and late in the day sun. Ideally, this is fully open for all 12 months, but if there is partial shading, if you've only got a window that's say from 10 o'clock to 3 o'clock or maybe 4.5 good hours of sun, we can usually make that work. Now, of course, you will be sacrificing some production, but you can still gather meaningful heat. We also need to be mindful of things like trees, knowing that they will grow, and that even though they lose their leaves in the wintertime, sunlight passing through a tree may not allow us to meet that minimum threshold. So sometimes, even though sunlight will be passing through, it's still not enough of it to actually get that collector up to that 100 degree range. One thing that we should note, though, is that minor obstacles like chimneys or an antenna or a light pole, which can be very problematic for solar electric systems, don't have the same sort of impact on solar thermal. If you've got a small shading in the bottom corner of the collector, the rest of the collector will be performing relatively well. Now, we would also prefer that the collectors face within 30 degrees east or west of true south. That's really our goal. That keeps us within about 5% of facing due south. So even if you're 20, 25, 30 degrees off, there isn't a huge reduction in the overall production. It's between 0 and 5%. And then even at about 40 to 45 degrees off, our reduction is only in the 5 to 10% range. It's when we get beyond 45 degrees that we really start to have problems. But like I said before in the collector mounting lecture, we will occasionally mount collectors facing due east or facing west, or sometimes both if you've got a peak that's running north-south, and then just increase the collector rate to compensate for that little bit of loss of production, which is generally about 25% if you're facing due east or facing due west. We would also like to pitch our collectors to be at an appropriate angle. The general collector pitch or tilt of the collector, if you are doing year-round production, we generally tilt it at your latitude. So I happen to be at about 45 degrees north latitude, so we will be pitching our collectors at 45 degrees. Now, this mediates between a low winter sun and a high summer sun, and the angle that the sun will be in the sky for us would be at about 45 degrees, making us perpendicular at that particular point. So if you are looking for a system that is trying to just produce the most in the summertime, like a summer pool heating system, or it's a summer use only, then we tend to drop that pitch down by about 10 or 15 degrees. So you take your latitude and you subtract off 10 or 15 degrees. So in my location, it would be about 35 degrees pitch. If you're trying to do space heating or domestic hot water space heating combination, then we tend to tilt the collectors up to a steeper angle, making them more perpendicular to a low winter sun. And so for us, we take latitude plus 15 degrees. And so in my case, that would be 60 degree pitch. To fully analyze your site and to make sure that you are getting enough solar radiation, the best method is to use some form of a shade assessment tool, whether it's the solar site selector, which isn't really made anymore, the solar pathfinder or solmetric sun eye. Both of those are good choices to figure that out. Here's a screenshot of a solar pathfinder, and ideally what you'd like to do is you'd like to take this sun chart and put it on a transparency facing south. The problem is there was a device that used that, and that was the solar site selector, but that little transparency would always blow off the roof and was very difficult to track and gather the data as well. So what this device does is it takes that sun chart and instead of putting the sun chart facing south, it reflects through this reflective dome everything that's in front of it and transposes it over top of the sun chart. What we typically then do is just take a picture of it, and there's a computer program that we can put this in there and it gives us our monthly percentages. So we're again looking for that 9 to 3 and then all the different months of the year. And that's what you see here. This is the times of day and then the different months of the year in these particular sun charts right here. These charts do vary based on latitude, so you pick a latitude range in which you fall in. The other thing that once we've selected a collector mounting location that has a sufficient amount of sun, sufficient surface area, and allows us to get the correct pitch, is then we have to try to track down the pipe run. It's generally pretty easy to figure out where we're going to put the solar storage tank because we would like that to be as closely located to our backup as possible. I tend to try to keep that within about 10 feet of your backup. But oftentimes the tricky part is connecting those two things. How do I connect my collectors down to my solar storage tank? And so we may be running, through attics, running through backs of closets. It is acceptable to run it along the exterior of a building as well. We want to make sure that everything is well insulated, and then we have appropriate pitch. In particular, if we have a drain back system, is it going to be suitable for that by having a constant slope going all the way back to the drain back tank? Now, one thing about placement of that drain back tank is that the closer that the drain back tank is to the collector, the less gravity you're going to have to overcome, the less static head that you need to overcome. So we have occasionally put those tanks in a closet on the second story, like in a bedroom closet that is a lot closer to the collector, and that reduced a lot of the head that we had to overcome with that particular pump. Now the next thing we want to do is to size the system, and sizing the system actually starts with doing a hot water load. Now we have an average here. The average American uses about 20 gallons of hot water per person per day. And by hot water, we mean water that is being used at 120 degrees. That's a gallon of hot water. So we're not calculating cold water consumption or total water consumption. It's just how much hot water do you use at 120 degrees. And that's an ASHRAE standard. Now, we've got a number of techniques that we go over in our site assessment class about how to refine this, but the easiest one to do at this level is to just use that rule of thumb. Now, this is a rough estimate, and we can modify it if you have particularly efficient appliances and you're particularly conservative or water conscious. We can always reduce that number down when we're doing the actual design and actual sizing. But just to give you a sense of how much hot water is being consumed, typical family of 4, 20 gallons per person, that's going to be about 80 gallons that they consume per day. Now, of course, there will be economies of scale. A family that has 5 or 6 people in it tends to use less water per person than one that's only 2 or 3, because there's certain things that you tend to do when you have more people living in a house. For instance, all of your loads of laundry are full, all of your dishwasher loads are going to be full. Since there's a line, people tend to take shorter showers, and so we certainly have some economies of scale there. We then use that water consumption to size the solar storage tank. Generally, the quantity of water that you use in one day will be the size of your tank. So we see something along these lines where I've got 2 occupants or 3 occupants, I'm going to have about 60 gallons per day. If you do have only 2 occupants, the numbers tend to be slightly higher, and we tend to use something around a 50-gallon tank. And with 1 occupant, we'll put in a 40, mainly because while they do make tanks smaller than that, it really isn't a cost-effective size to put in a really, really small system. So about the smallest size tank that we put in is about a 40-gallon tank. The idea here is that the tank should be sized to have your complete consumption in one day. Now, obviously, some days you'll use more hot water than the other, but on average, you'd like that tank to be equal to your total consumption. Then we try to figure out, well, how much collector do we need in order to heat up that 80-gallon tank of water, to heat up that quantity of water? And the simple rule is that it takes 1 square foot of collector to heat up 1 gallon of hot water. Now, this of course varies based on what your geographic region is. So a simple solution is about 1 to 1 1/4, but there are more defined charts. We have a full chart that's in my book that shows, based on which region you are, which zone you are, how many square feet of collector do you need to heat up a single gallon of water. So for instance, if you live in Arizona, you will be able to heat up about 2 gallons of water with a single square foot of collector. If you live in the Pacific Northwest, well, then you need about 1 square foot of collector will heat 1 gallon to 3/4 of a gallon, a little bit less, because you're going to be getting significantly less solar radiation. So as an example, using this particular standard rule, 80 gallons of storage would need somewhere around 80 to 64 square feet of collector. Now, those are some pretty standard sizes. We then have to figure out, well, how many collectors do I need to make that up? Well, standard collector sizes are something like 4x8s or 4x10s, or that 1 meter by 2 meter size. Or if they're evacuated tubes, they're sold by the number of tubes that are there, whether it's a 10 tube or a 20 tube or a 30 tube. A standard size for a 30 tube collector is about 5 feet by 7 feet, thereabouts, the tubes being 7 feet long and the header being about 5 feet long, which gives that a total size of about 35 square feet overall. So you're just trying to get close, because remember that we don't have collector sizes that are in 1 square foot increment. So that's why we have this range, and we're trying to get to about 64 to 80 square feet. Of course, if you have a more efficient collector, then you can get away with fewer square feet. Then we look at sizing some of these other components, and the pump sizing. And the way that we do that is we go through and we look at all the things that are going to cause resistance. So what is the pipe diameter, and what are the length, and the number of fittings and collectors and heat exchangers, and all these things that are going to cause some friction, and the overall amount of static head or gravity that it has to overcome if it's a drain back system. Now, it also determines on the target flow rate. The faster flow you have moving through a pipe, the more resistance you're going to have, and the harder that pump is going to have to work. So we also need to determine the flow rate. And generally, this is about 1 to 1 1/4 gallons per minute per collector, depending on what the square footage of collector it is. If it's a 40 square foot collector, we use a 1.25 gallon per minute kind of flow rate. You will also see on the SRCC data sheet some target flow rates and the flow rates that they used when testing. As far as that derating the flow for the glycol, it really just means that we need to increase the flow a little bit by about 10 to 15% when we have a thicker concentration of antifreeze. As we mentioned previously, drainback systems require a higher head, and pressurized systems just have the friction that they need to overcome. It says that that sizing heat exchangers isn't all that critical for the domestic hot water heating systems, and it's not that it isn't critical, is that the standard 40-gallon to 80-gallon tank with the embedded heat exchanger in it will always be sufficient for the 2-panel systems, 2 to 3 panel systems that we're putting on them. And generally, even a 2-panel system can get away with about a 5 by 12 heat exchanger that's only 10 plates, and sometimes only a 3 by 8 that's 10 plates. So some of the smallest versions of heat exchangers are pretty sufficient. Of course, it's always better to upsize this. There's marginal increases in price to get a slightly larger heat exchanger, and you don't want to have that be your bottleneck. So surface area and bigger heat exchangers is always something that we would like to err on the side of. And then finally, our design can be assisted with a lot of different computer modeling software. The most common one that's used is called RETScreen. It's Renewable Energy Technology Screening. It's developed by the Canadian equivalent of the Department of Natural Resources in conjunction with NASA weather data. And what they do is it's a simple, basic, glorified Excel spreadsheet that you put all your inputs in. You put in your particular geographic region, you specify your water consumption, your groundwater temperature, and then you select from the SRCC registry a particular brand of collectors. You specify the size of the collector array and the size of the storage tank. And then you define what your backup is. So your backup water heater, whether it's natural gas or electricity, how efficient it is, and then you define what costs you're paying for your current energy prices. And then it gives you all these excellent outputs. It'll calculate the annual energy production and the solar fraction that's going to be offset. It'll calculate the greenhouse gas reduction. And then, of course, it will calculate how much money it will save you and then do some projections based on an annual energy inflation rate and give you things like return on investment percentage and then your payback. The MREA has produced some YouTube videos about this that are posted on YouTube as kind of a step-by-step guide about how to complete that RETScreen and to do it satisfactorily. So you can find those there as well. We do give a full overview of RETScreen in our site assessment class because it is an essential component whenever you're providing a site assessment for a client. They're going to want to be looking at those prices. Now, there are a lot of other computer modeling programs that are out there, some that are much more accurate. One that I would recommend is one that's produced by the National Renewable Energy Laboratory, or NREL, and they have one called System Advisor Model, or just SAM for short. And that one is significantly more accurate, and they also have some webinars out there on how to use that particular program. So that's another one that I would recommend. Both of those are going to be free. There are some ones that you can pay for, like Transys or PolySun or TSOL, that are anywhere from $300 to $1,000 or so dollars, that will get you a little bit more precise. But at this introductory level, something like RETScreen or something like SAM is going to be an excellent tool to give us just a general sense of how these systems will perform. In terms of the maintenance that will be associated with some sort of a system like this, we do like to check up on it when it's sunny, right? Go ahead and you're walking by the system, take a look at the gauges, make sure that it has appropriate pressure in the system. That's the first thing that I look at. Has there been a leak? Look at the pressure, look at the pressure relief valves and make sure no fluid has shot out of there. The other thing that we're mindful of is the tank heating up when it's supposed to? You know, it was sunny all day. Is my tank 120 to 140 degrees at this point? And when it is sunny, going out and making sure that the pump is running at the appropriate time. Most differential temperature controllers have all these features in there, and oftentimes the differential temperature controller is installed down by the pump and all that stuff because it is helpful to have all that available when you're maintaining it or installing the system. But sometimes we have placed remote thermometers or wireless style thermometers that show the tank temperature up by where their common thermostat is. So the homeowner can just simply look and go, oh, well, my tank is at 120 degrees right now. And it's normally the thing that's kind of cool that they're interested in looking at. And then every 5 years, we've got a few things that we're going to want to inspect. We want to check the glycol and make sure that the pH is correct and that it has the correct freeze protection. So pH, we can test either using a digital pH meter or just some pH test strips. Very affordable, easy to find. The other thing we look at is the freeze protection, and the tool that we use for this is called a refractometer, and it looks at how the light refracts through it, and it will tell you what the percentage is, the glycol percentage, and what freeze protection level it's down to. Now, what wears glycol away are two things: contamination and overheating. And contamination, if the system was clean when the glycol was put in, if there wasn't a lot of flux or junk or dirt and debris left over there, and you don't have oxygen being introduced and anything that is going to rust away any ferrous components, then the glycol can remain uncontaminated for 30 plus years. If you do have any overheating issues, that's when you start to break down the glycol itself, and then it can become acidic. So the two things are really going to be contamination and overheating. If those two things are maintained at regular, consistent levels, then the glycol can last indefinitely. It isn't like the oil in your car that you need to change every 3,000 miles. This is the sort of thing that you're just checking it and then changing as needed. It is always good to check all the mounting hardware for tightness and make sure that you haven't had any flutter issues. One of the things that can happen is if the collector is, especially if it's standing up, when wind hits it can vibrate a little bit, which is okay, but the flutter can cause some of the bolts to loosen, and so we'll just want to check one of those. And then also check the roof or wall penetrations and make sure there aren't any leak issues, that all our roof boots and flashings are being well maintained. About 10 to 20 years, it says 15 to 20, but some of these things start to go a little bit before that. We want to check the pump and the controller and perhaps the expansion tank or drain back tank. Those are really the four maintenance components. The controller will have some relays that only have a certain number of cycles in them, but they can certainly last for quite a long time. And then the pumps can go out over time, especially if they have brushes. The newer pumps with the electronically commutated motors do not have brushes. They are brushless, and they should last a lot longer as long as there aren't any magnetic or rust issues that are associated with them. We may end up having to replace the solar storage tank, but again, that's a component that can last indefinitely as long as you change that sacrificial rod. These tanks have running through them that anode rod that is made out of that aluminum or magnesium that rusts before the tank does. Well, once it rusts away, well, then the tank is fair game. But if you check that, they will normally last 5 to 10 years. And replace that, in addition to flushing out any debris of the tank, then you can make one of these tanks last indefinitely. It's all about proper maintenance. You may need to replace some insulation after about 20 years, stuff up on the roof that we'd want to check out. But these are all relatively low-cost things that can make these systems last for quite a long time. So that, again, is just the overview of the system siting and design. I look forward to the next session.